Fill two identical cups with water. One hot, one cold. Put them both in the freezer at the same time. Logic says the cold one wins. It's already closer to freezing. It has less work to do. Sometimes it doesn't win. Sometimes the hot water freezes first. Not occasionally, not by some fluke of measurement error. Under the right conditions, reliably, the water that started hotter turns to ice before the water that started cold. This isn't a trick question or a magic trick. It's a real, documented phenomenon, and for most of modern science, nobody could fully explain it. It's called the Mpemba effect, and the story of how we found it, lost it, and found it again is stranger than the physics itself. So how does something hotter get colder, faster, than something that was already closer to the finish line? Let's get into it. The first thing to understand is that this isn't new. Aristotle wrote about it. Francis Bacon wrote about it. Descartes wrote about it. Some of the sharpest minds in history noticed that hot water seemed to freeze faster than cold water. And then, for centuries, the observation basically got shelved, filed under probably wrong, and forgotten. Here's where it gets interesting. In 1963, a Tanzanian high school student named Mpemba was making ice cream. He noticed his hot mixture froze faster than his classmates' cold mixture. He asked his physics teacher why. The teacher told him he was wrong, that what he saw wasn't possible. Mpemba didn't let it go. He kept asking. Eventually, a visiting physics professor named Dennis Osborne actually tested it instead of dismissing it. And Mpemba was right. The effect was real, and it now carries his name. So what's actually happening in that cup of water? There isn't one single answer. There are several mechanisms that can stack together, and depending on the conditions, different ones dominate. Evaporation is the biggest one. Hot water evaporates faster than cold water. As it evaporates, the total volume of water shrinks. Less water means less mass that needs to be cooled down to reach freezing. You're not racing the same amount of water anymore. The hot cup is quite literally losing content as it goes, giving itself a head start it wasn't supposed to have. Then there's convection. Hot water develops stronger internal currents as it cools. Warmer water rises, cooler water sinks. And this constant circulation means the entire volume loses heat more evenly and more efficiently. Cold water, by comparison, cools from the outside in, forming an insulating layer near the surface that actually slows the process down. The hot water is stirring itself. The cold water is trapping itself. Dissolved gas plays a role too. Hot water holds less dissolved gas than cold water because heating drives gases out of solution. Less dissolved gas changes the water's properties slightly, including how efficiently it can transfer heat, and some research suggests this makes it easier for the hot water to lose energy quickly. And here's the one almost nobody expects. Frost. When cold water sits in a freezer, it can build up a layer of frost underneath the container itself. Frost is an insulator. It slows heat transfer between the container and the freezer surface. Hot water containers, because of how they interact with the surrounding cold air, are less likely to develop that same insulating frost layer underneath. The cold water can end up sitting on its own natural blanket, while the hot water has a clear path to keep losing heat. None of these factors alone fully explains the effect every single time. That's actually why the Mpemba effect took so long to be taken seriously. Scientists kept trying to find a one true cause, and there isn't one. It's a combination, and the specific mix that wins depends on the container, the amount of water, the freezer conditions, even the surrounding humidity. This is also why the Mpemba effect doesn't happen every time you try it. Change the container shape, change the volume, change how the water is exposed to air, and the effect can vanish completely, or even reverse. It's not that the physics is unreliable. It's that this is an incredibly sensitive system, where several competing processes are racing each other, and small changes in setup decide which one wins. Here's the part that should genuinely surprise you. In 2016, a team at Nanyang Technological University proposed something that went even deeper. They suggested the initial temperature of water changes the actual structure of the hydrogen bonds between water molecules before any freezing even begins. Hotter water molecules are pushed slightly further apart, and when the water cools back down, that molecular rearrangement may release energy faster than water that was never heated in the first place. If that holds up, the effect isn't just about evaporation and convection acting on the outside. It might be baked into water at the molecular level. And this is where things get genuinely unresolved. Some physicists argue the Mpemba effect, at least in a lot of common experiments, isn't a single clean phenomenon at all. It's a mix of the mechanisms we just went through, showing up differently depending on exactly how you run the test. Other researchers insist there's a deeper, more fundamental explanation still waiting to be nailed down. As of right now, there is no single peer-reviewed consensus that closes the case. That's honestly a strange place for science to be. A high school student in 1963 asked a question so simple a teacher assumed he was wrong to even ask it. And more than 60 years later, physicists are still actively publishing papers arguing about the real cause. So the next time you're filling an ice tray or waiting for water to freeze for whatever reason, remember what's actually happening in that cup. Evaporation, shrinking the volume. Convection, stirring the heat out. Dissolved gas escaping. Frost building or not building underneath. And possibly, just possibly, the very structure of the water itself, remembering that it used to be hot. Simple question. Still no final answer. So here's the question for you. If you tried this at home, right now, hot versus cold, which one do you think would win? Yes, hot wins. Or no, you think cold takes it? Drop your answer below.